When you step inside a medieval hall, cathedral, or farmhouse that has stood for centuries, you're greeted by something astonishing. Above your head, immense wooden beams arch with dignity, supporting roofs that have seen countless seasons, storms, and even the passage of history itself. In stark contrast, modern homes, even those built in recent decades, often suffer from sagging beams, bowed roofs, and structural surprises that reveal themselves far too quickly. Why do these relics of the past endure, while so many newer constructions falter and fail? The answer isn't just about materials, but a complex web of forest wisdom, clever joinery, a respect for natural limits, and a different mindset about what it means to build for permanence. Today, we uncover the secrets behind why medieval beams still hold their roofs. It's a story of craftsmanship, science, ecology, and forgotten techniques that deserve rediscovery if we hope to build homes that endure for generations. Before a beam was even hewn, a medieval builder understood wood as a living entity, not just a commodity. They spent their lives surrounded by old-growth forests, ancient stands of oak, ash, chestnut, beech, and fir that grew slowly over centuries. The properties of these slow-growing trees would define the longevity of their buildings. Medieval craftsmen were remarkably selective in tree choice. They noticed which trees grew straight, which had natural curves, which woods resisted rot, and which withstood immense tension or compression. Oak, in particular, was highly prized, not only for its strength and workability, but for its high tannin content, which gave it a natural resistance to insects and fungal decay. Areas with abundant curved oaks inspired the innovation of the cruck frame, where two curved timbers would be paired to form an arch, distributing weight to the ground and eliminating the need for central posts. Tree harvesting always had seasonal timing. Most carpenters felled their timber between late autumn and winter, when sap was low and humidity inside the wood was minimized. This reduced future shrinkage, warping, and cracking during the drying process. Any sap or moisture remaining would gradually acclimate out, seasoning, sometimes years long, that instilled patience into every project. Lumber was never randomly cut. The fellers oriented their beams with keen understanding of a tree's grain, applying medieval geometry knowledge to cut with, not against, the natural lines of strength within a trunk or limb. Trees with gnarly, twisted growth were prized for specific uses, like braces and wall ties, where pre-existing strength or angles could be harnessed, not wasted. Curved timbers made cruck frames possible, creating self-supporting wooden A-frames that still stand after centuries. Once harvested, medieval beams were often left massive. Without modern milling machinery, laborers shaped with axes, adzes, and broadaxes, trimming away bark and waste, but leaving beams thick and robust. Unlike modern, stick-built homes that use dozens of slender, matchstick-like boards for a roof, medieval roofs were constructed on a smaller number of large, weighty timbers. A single medieval tie beam could measure a foot or more across and span the width of a great hall. Rafters, principal posts, collars, and king or queen posts gave a roof not just structure, but weight, resisting the uplift of wind and reducing vibration from storms. This massiveness was not just about overbuilding. Larger sections weathered rot more slowly, dried more evenly, and held up under heavy snow loads, which, without central heating to melt them from below, could linger all winter long. The thickness of the beam also allowed superficial cracks, checks, to develop safely over time without jeopardizing the timber's core integrity. Even as the outermost layer aged, shrank, or even weathered off, The inside remained dense and strong, a slow, deliberate sacrificial system that allowed beams to age with grace. Perhaps no aspect of medieval timber construction is more celebrated than the art of joinery. The ability to connect massive beams without nails, bolts, or modern metal fasteners. Medieval builders employed mortise and tenon joints, in which a projecting tenon at the end of one timber fit snugly into a mortise or slot carved in another. These joints could transmit both tension and compression forces and, when combined with hand-carved wooden pegs, called treenails or tree nails, would tighten over time as the wood expanded and contracted with seasons. Scarf joints allowed two beams to be joined end to end, enabling long spans from shorter trees. Lap joints, dovetails, and half-laps were carefully carved to maximize mechanical strength and minimize weak points. The geometry of these joints, often passed through generations of apprenticeship and oral tradition, accommodated seasonal wood movement. Unlike rigid metal fixings, which could force beams to split or shear as the timber dried and contracted, wooden joints subtly flexed, absorbing the natural ebb and flow of timber as it lived on, even inside a building. Curved braces strengthened every junction. Roof trusses often took on intricate triangular or arch shapes, converting lateral forces into vertical compression, further distributing live and dead loads safely to the ground. Many of these techniques were dictated by necessity. Iron was costly and often reserved for nails in minor places, if used at all. Yet the science embedded in the absence of nails remains profound even today. Let the wood be wood. Let it breathe and shift, and it will last. This system also allowed for repair and replacement. If a joint failed or a beam succumbed to rot, it could be carefully replaced without bringing down the rest of the roof, a kind of built-in maintenance cycle foreign to most modern construction. Medieval builders were pioneers in structural geometry. The challenge of spanning broad spaces, like the nave of a church or a noble's great hall, required more than brute strength. It demanded systems that distributed weight and resisted deformation from varying loads. The result was the truss, a structure composed of beams organized into triangles, which, as engineers know, is the most stable shape in architecture. Triangular trusses transfer roof loads efficiently to the supporting walls and foundations without creating bending moments that lead to sagging. In many medieval roofs, tie beams stretched between walls, while principal rafters rose in steep pitches, often meeting at a central ridge. King and queen posts extended vertically from the tie beam to the rafters or ridge, countering downward forces and limiting flex. Added braces, angled diagonals, supported corners and joints, helping the frame resist twisting, wind loading, and splaying. Beyond pure triangles, special truss forms evolved. Hammer beam roofs with ornately carved short beams projecting from walls allowed even broader spans by cantilever and bracing. A hammer beam roof like that in Westminster Hall can span over 60 feet without central supports, thanks to careful balancing of opposing forces and redundancy at every crucial juncture. Complex joinery at truss apexes and connections allowed gradual settling without catastrophic sagging. When a beam did compress or warp, the geometry of the frame redistributed stress invisibly. Any deflection was spread over many members, leaving the overall shape stable, whereas modern stick roofs, loaded disproportionately on a single weak rafter, can fail suddenly. Seasoning is a key word in medieval durability. Medieval beams were air-dried over months or years, sometimes on site, sometimes in the forest itself, before final shaping and assembly. This allowed moisture to slowly depart the timber, shrinking it gradually, building up dense, stable heartwood resistant to warping, splitting, or future movement. Builders knew that working slightly green oak was easier, allowing the final fit to tighten as the wood finished drying in place. This produced joinery that creaked and groaned in the first few years, but ultimately locked tighter over time. Medieval roof systems also incorporated air spaces to allow beams to breathe. Gaps between roofing tiles or thatch let vapor escape but kept water out. The absence of vapor barriers, so common in modern houses, meant fewer pockets of trapped moisture and less risk of decay. Roofs were steep, quickly shedding rain and snow, and projecting eaves and gables helped keep supporting walls and timbers dry. This holistic approach to moisture meant that even in centuries of wet and variable weather, beams endured. Not all timber is created equal, and medieval carpenters knew it. Oak, loaded with tannins, resists rot and most insects, especially when exposed to variable humidity and decay conditions. Heartwood, formed as the inner, non-living part of the tree, was prized above sapwood. Heartwood contains concentrated natural chemicals that retard fungal and insect attack, endowing longevity. Builders often used heartwood for principal timbers and large beams, relegating sapwood to less vital applications. Other species, chestnut, beech, fir, and pine, were used locally, but seldom for primary supports. Over time, villagers also realized that the environment in which a tree grew, soil, climate, density of forest, would affect the final quality of a beam, leading to timber selection and even cultivation specifically for structural purposes. The story of medieval beam endurance is also a story of stewardship. Carpenters and owners treated a roof as a living organism requiring regular care. Leaks and broken tiles were immediately repaired. Thatched roofs were routinely relayered, patched, or replaced, a form of ongoing insulation and waterproofing as well as beam protection. Beams were sometimes oiled, tarred, or limed. Church roofs, for example, might receive a wash of lime solution to discourage rot. Roof timbers were ventilated, with open eaves or clear stories circulating dry air, discouraging condensation. Periodic inspection was a community activity, especially before winter storms. It was common for beams to be redressed, smoothed with adzes or planes to remove surface decay, then left solid again, extending life almost indefinitely. In modern construction, speed is everything. Lumber is grown quickly in plantations, often in as little as 20-40 years, compared to the centuries-old oaks felled in medieval times. Fast-grown wood is lighter, with wider growth rings, more knots, and weaker overall structure. Kiln drying, done for speed, can set internal stresses or leave wood vulnerable to sudden moisture changes. Modern dimensional lumber is also cut much thinner, optimized for cost, not longevity. Joinery is almost an afterthought. Most roofs are held by metal plates, nails, or bolts, all of which can become failure points. Metal connectors are inflexible and concentrate stress, so beams may split, pulling away from fasteners, especially as wood shrinks or swells with seasons. Metal also corrodes over time, expanding and exerting pressure that can crack beams. In hidden locations, moisture and rot can set in, leading to unexpected failures. Beams are seldom oversized. In a modern truss, even the primary load-bearing members are small by medieval standards, and redundancy is minimal. A failure in one rafter or connector often leads to chain reaction collapses. Worst of all, modern buildings often seal beams away from airflow. Without the ability to breathe, even well-constructed modern wood is at risk for rot, mold, and insect infestation. ordinary repairs are often ignored or delayed, allowing small problems, moisture intrusion, tiny cracks, to balloon rapidly. Sagging begins as soon as beams are loaded beyond their capacity to recover. In modern methods, this might mean slight warping due to insufficient sizing, improper placement, or lumber defects. Over time, creep, permanent deformation due to sustained loading, sets in. Thermal cycling introduces expansion and contraction. If beams are not allowed to move individually, or if they're forced by rigid joints, microfractures form. Water ingress through roof leaks accelerates decay, undermining strength, and a once flat roof develops visible dips and waves. Once sagging sets in, loads shift to other beams in ways not anticipated by the original design. This cascade can trigger widespread failures, even in relatively young houses. Contemporary architects and engineers increasingly study ancient timber methods to design longer-lasting buildings. Slow growth, dense wood is making a comeback for specialty projects. Mass timber construction, using glulam and cross-laminated timber with oriented grain, seeks to combine traditional robustness with modern efficiency. Engineered joinery, sometimes borrowing from centuries-old mortise and tenon systems, is now prized in high-end green building. Timber frame revival movements use massive beams, hand or CNC milled for precision, locked with wood pegs, and designed for future repair, not simply demolition. Ventilation, maintenance, and integration of tradition with technology are again recognized as key ingredients for structural health. Wander through Europe, and you find countless examples of medieval timber mastery. In England, the ancient tithe barns of places like Bradford-on-Avon and Great Coxwell still stand, their beams over 600 years old. These cathedrals of the countryside feature titanic tie beams, intricate cruck and king post trusses, and collective wisdom of repair and adaptation. The hammer beam roof of Westminster Hall, completed around 1400, is perhaps the largest clear-span timber roof in the world, a marvel of architecture that has weathered fire, war, and the relentless London fog. In France, the market halls of Normandy, or the great beams of Paris's Notre-Dame de Paris, which survived even after devastating fire in 2019, stand as a testament to strength and adaptability of oak roof structures. In Germany and Switzerland, whole towns are filled with timber-framed houses, Fachwerkhäuser, whose primary structures date to the Middle Ages, the careful joinery of beams and braces a lesson in thoughtful design. Even the wooden stave churches of Norway, made with elaborate interlocking frames, remain standing after a millennium. These buildings have not avoided decay altogether. Beams develop checks, splits, and surface rot. But as long as maintenance is upheld, compromised elements can be replaced, and the structure lives on, sometimes for as long as human civilization continues to care. Medieval societies expected their buildings to last for generations, if not centuries. They built accordingly, investing more labor, better materials, and systems for monitoring and repair. Modern homes are built for different expectations, often for quick sale and fast profit, and rarely with thoughts of lasting 3 or 4 generations. But as our world faces new resource constraints and environmental instability, the lessons of medieval builders about sustainability, care, and durability become ever more essential. The combination of wise material selection, massive sizing, flexible and robust joinery, strong geometry, and ongoing stewardship explains why medieval beams still hold roofs secure. To truly understand why medieval beams outlast their modern descendants, you must respect both the material and the intent. A medieval builder wasn't just assembling a roof to keep out the rain. He was working with nature to craft something lasting, something future generations would inherit, repair, and celebrate. This mindset, forged in the forests and workshops of the past, produced buildings that are both humble and exalted. It's not only the secret of strong wood and clever joints, but of patient labor, attention to small failings, and a cultural respect for repair. As we look to the future, whether we are building homes or restoring historic halls, we have much to learn from our ancestors. The secret is not just in the brawn of heavy timbers, nor in the science of beams and trusses, but in a world view, a recognition that good buildings are grown with time, made with care, and maintained with reverence. If you want your roof to last centuries, start by respecting the wood beneath it. Understand its needs. Design for movement, for breath, for repair. Build not for today, but for the long arc of history. That's the enduring wisdom, the genius in old beams, and the challenge for anyone who dares to build with the generations still to come in mind.